Disclaimer: the following AR-15 Rifle 223 performance analysis is for educational and/or engineering specification purposes only. I, Mark D. Scythian, am not responsible for viewer use, misuse, and abuse of the following thermoballistics data presented in this performance analysis. Welcome to this AR-15 Rifle 223 performance analysis. My name is Mark Scythian. The date today is October 17, 2022. So this particular performance analysis will focus on the optimized barrel length for the AR-15 223 of 16 inches and the ammunition specifications: 55 grains bullet mass and 25 grains smokeless gunpowder charge mass. The ammunition dimensions are specified in this graphic here. So the analysis outcomes will include points 1 through 9. So the first step is to compute the effective barrel length, which includes the concealed linear length of the bullet pressed into the shell neck. So the sequence of events after the trigger is pulled is that the firing pin strikes the sodium azon primer. This then sets off the solid smokeless gunpowder and converts it into a pure gas through exothermic sublimation. So an example of sublimation is when a solid converts into a pure gas. And in this case, heat is released, so it's exothermic sublimation. And so the ratio between 1 gram of smokeless gunpowder mass to gas production is 1 gram smokeless gunpowder will convert into 342 cubic inches of gas. So you can imagine the amount of pressure that builds up in the effective shell volume, which is the cylindrical volume including the conical taper volume, which induces a dynamic pressure spike as well. So this then concentrates at the back of the bullet, its cross-sectional area. The pressure times the cross-sectional area will yield the force, the horizontal dynamic force, which then accelerates the bullet out of the shell neck, overcoming the interference fit, and then pushing the bullet out through the barrel, for which the lands and grooves, the rifling, cuts into the bullet, causing it to spin to maintain rigidness in space. And after the bullet exits the barrel and enters the atmosphere, it is then subjected to the downward gravitational vector and the aerodynamic drag. So this particular shape bullet will have an aerodynamic drag coefficient equal to 0.295. Now, if this was a ball bearing, the aerodynamic drag coefficient would be approximately 0.5. So with that information, we can go down here and then compute the effective shell volume in two sections. One is the conical taper volume, which is solved by using the volume of a truncated cone formula here, and the volume of a cylinder formula here. So we take the dimensions of the cylindrical and conical shell structure and we make the calculations. So this then yields a total effective shell volume equal to 0.18 cubic inches and a shell taper pressure ratio equal to 2.52 to 1. So now we have all the information to complete the analysis, points 1 through 9. So assume we are firing the AR-15 223 at an elevation of 880 feet above mean sea level, which means that the atmospheric pressure will equal 14.24 psi. There are 1.62 grams of smokeless gunpowder in the shell. Each grain is equal to 64.8 milligrams. So immediately after the trigger is pulled, the 1.62 gram smokeless gunpowder charge will convert into 544 cubic inches of gas volume within an effective shell volume of 0.18 cubic inches. So this then creates an atmospheres above atmospheric pressure, ATMs, then multiplied times the atmospheric pressure, and then multiplied times the shell taper pressure ratio, which will incur 110,445.4 pounds per square inch gauge pressure above atmospheric pressure within the effective shell volume. This then is multiplied times the bullet cross-sectional area, so 0.223 inches. We solve for the cross-sectional area using pi r squared, which is equal to 0.039 square inches. So when we multiply the effective shell pressure times the bullet's cross-sectional area backing, this will incur 4,307.4 pounds of force, accelerating the bullet out of the shell neck. The bullet mass is computed at 0.0035 kilograms, converted from grains to milligrams, then grams, and then kilograms. So next we access Newton's second law of motion. Force is equal to mass times acceleration. We then convert the 4,307.4 pounds of force horizontally accelerating the bullet. We convert this value into the Newton's force metric equivalent of 19,168 Newton's force, and then we divide this into the kilograms mass of the bullet to compute the bullet's acceleration, which is equal to 5,476,571.4 meters per second squared. The next step is to compute the bullet's acceleration time, so we have to convert the effective barrel length into meters, and then we can use the acceleration is equal to distance divided into time squared formula, and then solve for the time component by taking the square root of the ratio of the effective barrel length divided into the bullet's acceleration. So this then yields a bullet acceleration time equal to 0.000277 seconds. When we multiply the acceleration times the time of acceleration of the bullet, we compute a muzzle velocity equal to 4,975.7 feet per second muzzle velocity, or 1517 meters per second. However, the bullet will slow down somewhat when it enters the atmosphere, as aerodynamic drag is subjected to the projected frontal area of the round. So we can subtract 0.295 from 1 because it is a coefficient with dimensionless, unitless values, and multiply this times the muzzle velocity. So the constant velocity from discharge of the barrel to the target will equal a bullet velocity through the air equal to 3,508 feet per second. So what is practical is to compute the gravitational drop of the round if the rifle is fired horizontally over the ground at approximately 4.5 feet above ground level. So we can use the delta y is equal to 1/2 GT squared formula, converting the units into metric values. So this then becomes the distance above ground level in meters, then divided into 1/2 g and its square root. So 0.77 seconds is the time it will take for the bullet to drop 4.5 feet on the vertical axis. So this then equates to an effective line of sight bullet range of about 2,700 feet. Although the 300-meter rule is the practical line of sight range, because it isn't the velocity that curtails the effective range, it is the gravitational drop. So we're talking about practicality here. So we'll say the effective line of sight non-scope range for practical shots is between 1,100 and 2,700 feet, unless you change the entire shooting platform to an inclination and highly controlled scope metric, because then you can volley the bullet much farther by increasing the elevation. But this is just a general calculation for line of sight non-scope applications. So we're looking at 1,100 to 2,700 feet effective range for horizontal shots, compensating for the gravitational drop. The bullet impact force in pounds is the negative velocity of the bullet after it hits the object, the target. There'll be a rapid reduction in speed to a theoretical 0 feet per second. This negative velocity in feet per second is then converted to meters per second and then divided into the instantaneous time, which is a value very close to 0, but we cannot divide into 0, so this becomes an instantaneous time. So this calculation here computes the instantaneous deceleration or negative acceleration multiplied times the bullet mass and then converted back into pounds force. So the bullet impact force in pounds is equal to approximately 841 pounds of bullet penetrating impact force. So if we use that value to compute the bullet penetrating pressure, it is simply the bullet impact force divided into the bullet's cross-sectional area. So we have approximately 21,570 pounds per square inch for penetrating pressure, which then, of course, leads to the fragmentation of the round, which the AR-15 and the M16 are quite popularly known to be fragmentation rounds due to the high bullet penetration pressure. The bullet collision impact power, assuming an inelastic collision, as in the previous calculation, as in the bullet does not ricochet but goes one way and penetrates, we then have a collision impact power equal to the pounds force multiplied times the instantaneous distance. That would be theoretically 0 or close to 0. So we're assuming right after the bullet had hit the target that the distance it will travel thereafter is 0, but we can't multiply times a 0. So we take it to an instantaneous distance value of 0.01, and then we divide this value, this product, into the instantaneous time. So the kilojoules that are listed for this round are approximately equal to 3,700 watts of collision power. And then lastly, we have the ballistic discharge power. This is the power involved in accelerating the bullet through the barrel. So we know that power is the force times distance, the foot-pounds, or the Newton meters. And when we divide the work, force times distance, into time, this is when we get power. So if an X amount of foot-pounds of work is carried out in less time, then the power goes up. If an X amount of foot-pounds work is carried out in more time, then the power goes down. So that being said, we take this large amount of foot-pounds per second and multiply it times 0.737 foot-pounds per second, which is equal to a watt. This is because 1 Newton meter, 1 Newton of force moving 1 meter is a joule, and then 1 joule per second is a watt. So there's 0.737 foot-pounds per 1 Newton meter of work, or 1 joule of work. So therefore 0.737 foot-pounds per second is equal to 1 watt. So we can take this large foot-pounds per second mechanical power value and multiply it times 0.737, and the ballistic discharge power, or the power accelerating the round in the barrel, is approximately 16 million watts, or 16 megawatts, hence high-powered rifle. So all points 1 through 9 have been solved, and here are the specifications, the calculated specifications for the calculated performance specifications for the AR-15 223 rifle using the 16-inch barrel, and ammunition specifications: 55 grain bullet mass and 25 grains smokeless gunpowder charge mass. Thank you for watching this performance analysis, and have a great day.